It drives me nuts. Our food specialists insist on giving us the same number of chocolate, vanilla and butterscotch puddings when the laws of physics dictate chocolate will disappear much faster. No one's going to get a vanilla craving in space or on Earth.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Scott Kelly there with some wise words of wisdoms. I'll tell you what though, Matt, I bloody love a butterscotch pudding, me.
Oh my God, butterscotch is my favourite.
I'll tell you what, you can keep your chocolate. I'll take your butterscotch pudding.
Butterscotch Angel Delight is perhaps my guilty pleasure. I absolutely love that stuff.
Oh my God.
As do my kids. And we have it all the time. It's our special bonding moment after supper.
Do you reckon we'll get sent some butterscotch now we've given it such a big shout out?
We should do. We should make a sort of space version of it.
Space butterscotch. Sounds like something you could get in Amsterdam.
It's Mark and Scott Kelly's birthday today, Jamie.
Happy birthday, the Kelly twins. Pair of leg ends.
And it's also Cephus Calvisius, a German astronomer and composer.
Wow.
It's his birthday too. And of course, George Hale, who was the discoverer of magnetic fields in sunspots.
Well, happy birthday to both of you.
He obviously helped build loads of huge telescopes. That's what he's most famous for.
Yeah, that doesn't hurt either, does it?
No, making Caltech a kind of leading centre of astrophysics and cosmology, etc.
Matt, we're the leading centre of the space podcast world, aren't we?
Yeah. Jamie, I have got an awesome interview for this episode.
You better have, because tell you what, we've been interview dry, so it better be a good one.
It is. It's with Professor Jim Al-Khalili.
Professor Jim. Wow.
And as you know, Jamie, he's one of my favourite science communicators of all time.
Oh, wow.
I shall be sticking his video of the explanation of Maxwell's demon in the notes because I think it's absolutely awesome. And of course, it applies to that, an episode a couple of weeks ago. But yeah, no, it's a really good interview. I really enjoyed going up to his office on the Surrey University campus. He's a really, really nice, down-to-earth guy.
Oh, I can't wait to hear it.
He's got a new book coming out called The World According to Physics, where he covers all the stuff that we've been talking about recently on the podcast. So I can't wait for that. That comes out on the 10th of March.
Have a look out in all good bookshops.
He also, and this one I didn't know, he's recently brought out a sci-fi called Sunfall.
Wow.
Do you want the synopsis of that? Because it's quite cool. In 2041, and the world as we know it grinds to a halt. Our planet seems to be turning against itself. Earth's magnetic field is failing. World governments have concealed this rapidly emerging Armageddon. But a young Iranian activist stumbles across the truth, and it becomes a race against time to reactivate the Earth's core using beams of dark matter.
Sunfall. When's it out?
That's already out. That sci-fi book's already out. I just didn't know it existed, so I'm downloading it right away on Audible for a good old listen. But I love the fact that he's speculating what the candidate for dark matter is going to be found out to be, and I love that whole idea that, of course, in say 10 years' time, when we do discover what dark matter is, he's going to be able to say, "Yeah, I was writing about that 10 years ago."
People seem
if he gets it right, it's like a gamble, isn't it?
It really is a gamble. People seem to be really excited by our dark matter show, Matt.
Yeah, absolutely.
I think dark matter is on fleek.
Yeah, no, absolutely. And I think that the two things that we covered in dark matter, and I will repeat this, they are so speculative and fringe. But as we'll hear from Jim Al-Khalili, these fringe ideas are becoming more and more emboldened all the time. We actually don't find what dark matter is in the sort of more reasonable sense of that it is some form of exotic matter made from axions or neutralinos or one of these sort of things. So it's an exciting time to be alive, as we'll hear from Jim in a minute when we play the interview. But I wanted to also cover something that I thought was really popular this week.
Wow, okay.
And that was a little post I did about space mirrors that both went a little pretty wild on Twitter and on Instagram. People loved it. So I thought I'd talk about it. And it kind of ties in with Jim Al-Khalili as well, because I was listening to Jim Al-Khalili does a BBC podcast called The Life Scientific, and he interviewed Miles Allen, who's like a super expert in global climate change, and it's a really great podcast if you want to listen to it.
Nice.
And at that point, they call it during this podcast, they call it a climate emergency. And of course, we know all about climate emergencies at the moment and the effect that's having on politics and Extinction Rebellion, which we may talk about a little bit later on in the show. And it got me thinking about what solutions and actions we should have for that kind of...
Yes, what can we do? What can our listeners do about it?
Well, I don't know what our listeners can do about it. I mean, this is a global problem. It's global warming, not Jamie's house warming.
Yeah, but
although we still haven't had that, had we? We still haven't had the Jamie's house warming party.
Every little person can make a difference, including me and you.
Oh no, absolutely. I totally agree with that. And actually, what I'm about to say about, I mean, there's really two or three prongs of attack, isn't there, with global warming? We need to do something about the carbon that we're releasing into the atmosphere.
Yes.
And we've just got to basically reduce that and get it down to at least zero emissions, if not some form of,
some form of
getting
plus.
Some of that carbon,
exactly,
sort of getting some of that carbon back out of the atmosphere. However, there is another strand to this strategy, which is geoengineering. There's a little bit of reticence about geoengineering because of the people don't see it as being the solution. But I would say to you, Jamie, imagine if you were ill. Say Jamie Franklin had got a little bit fat.
Too much butterscotch, instant whip.
Yeah. And you were suffering from a condition caused by obesity. Now, there might be a medicine available for you that would mitigate some of those symptoms. Agreed?
Agreed.
But what we ideally want to do is get your addiction to butterscotch instant whip down,
yes,
and start you on a healthier lifestyle.
Yes.
Well, I kind of equate that to these two different. So the geoengineering is a bit like this plaster that we're giving you, or the medicine that we're giving you to mitigate some of your symptoms. But of course, the ultimate solution is to get you exercising and off the carbon.
Yes,
if you know what I'm saying. So I think that geoengineering should play a part in this. That we've got a sick planet at the moment, and we need to start thinking about ways that we can geoengineer. And my favourite, of course, is to build a machine that makes pristine sheets of graphene while taking that carbon out of the atmosphere. So it like double whammy of like super amazing tech while clearing up the atmosphere. Be amazing, wouldn't it?
That'd be killing two space birds.
So can someone please invent that? But one thing that came up as a geoengineering solution quite recently. Do you know Andrew Yang, the presidential hopeful who's now dropped out of the race? So he... Actually, I think he's one of the very first candidates who ever talked about geoengineering as part of his climate change policy.
Okay.
Which is literally in direct opposition of Bernie Sanders, who's ruled out nuclear, geo, and carbon capture technologies altogether in his Green New Deal. So it was interesting that Andrew Yang brought it up, and it was good because it's kind of slightly put it back in the agenda. And he kind of proposed $800 million budget for research into geoengineering solutions. And of course, one of these is the space mirror.
Yes.
And the space mirror essentially is there to increase Earth's albedo. And albedo is that ability to reflect light. And
not libido.
not your libido, your albedo.
Got it, okay.
And yes, so yes, if you put a bunch of mirrors in space, you can reflect away some of that light that was going to enter the atmosphere and heat it up a little bit. So that's essentially it. So the basic principle is put a mylar sail into space that blocks the light or reflects the light on a place on Earth that you might need it. So you can use it both ways. You can use it to block light or reflect light. And this idea, actually, you'd think this idea had been around for much longer, but it seems like the idea first sort of came out in the early 80s when they were thinking of ways of cooling Venus down with geoengineering. But by 89, there was a chap called James Early who works for the Lawrence Livermore National Laboratory who started proposing building a huge space shade at our favourite Lagrange point L1.
Oh, yes.
To cool Earth down. And he proposed that this thing would be insanely expensive in the sort of trillions of dollars range. And perhaps you'd have to make it on the moon because it would require too many space launches. It had started to come onto the agenda. Now, there's this guy called Lowell Wood. And I don't know if you've ever heard of Lowell Wood, but he's got a PhD in geoengineering.
Okay.
But his most amazing thing is that he's the most prolific inventor in US history. In other words, he holds more patents than any other US citizen.
More than Edison.
Even more than Edison. So
Get
yes,
out.
I believe Thomas Edison is second and Lowell Wood is first.
Jeez.
And he's part of another company called Intellectual Ventures that sort of hoover up all these patents. They're slightly sort of controversial, but they have a geoengineering tech department and a global good department where they work with people like Bill Gates. But Lowell Wood, this PhD in geoengineering, reckons you only need to reflect about 1% of the sunlight to start getting the climate under control. This would be a little bit of medicine. Build these things, get the thing under control while we sort out our addiction to oil, essentially, and burning fossil fuels. It would require a 600,000 square mile. I mean, think about that. 600,000 square mile sheet of mylar blocking out the sun. But you could do it with lots and lots and lots and lots of small ones, wire mesh mirrors.
Patchwork, yeah.
But if you think about it, if you were doing it with, say, hundreds of thousands of little satellites, think about that cost and think about, like, you kind of balk at the idea that it's just too difficult. But then you think, what about cars? There's a single car factory that can churn out hundreds of thousands of cars that are way more complicated. And things like building seawalls and all the other things that we're going to have to do with global temperature rises, maybe the cost actually isn't as bad as you think. And I also think things like Starship. One of the most interesting facts I've heard for ages, Jamie, is that the space elevator actually wouldn't be as cheap as Elon Musk is saying Starship is per kilogram of mass that you're getting into space. So it kind of makes the space elevator completely useless. Like getting rocket launch systems as large as Starship and reusable actually makes getting stuff into space a lot cheaper. So maybe with the advent of Starship, and if that sort of came online, getting hundreds of thousands of these mylar sheets into space wouldn't be that bad.
But what about the astronomers?
Well, there's huge downsides to this technology. Now, the one that I think a lot of people sort of spring to mind is the evil genius that's using geoengineering to hold the world to ransom. But the risk of weaponizing this is actually pathetic, and I love the analogy. I think it was Isaac Arthur that came up with this analogy where you have basically you don't give all your soldiers hand torches to get them to point their torch at one other soldier and see if you can burn him.
Yeah,
it just doesn't happen. No. There's so many more effective weapons. And essentially the whole world is now booby-trapped to utter destruction with nuclear bombs. So the ship has sailed when it comes to geoengineering weapons. They already exist. We're already in that paradigm. So let's not worry about that. And anyway, they just aren't that kind of thing. You just can't really use them for weapons. But an interesting thing about them is you could beam sunlight onto certain areas, say parts of these Scandinavian countries that are dark all the time, or parts of Siberia that are dark all the time. You can beam down sunlight, but take away the infrared element of it. And so the sort of global warming aspect of that sunlight now has disappeared, but you're actually giving some use down on the ground as well. So there's some like really interesting ideas. So
I'm sure the people of Siberia would be very happy.
Well, they actually very well might be. And we'll actually get onto something that was, the Russians have taken this very, very seriously, which was actually the topic of my Instagram post. But let's just finish like thinking about some of these other things. So
yes,
if you had this massive array of sunshades that are blocking out 1% of the light to get global climate change under control, you wouldn't even notice it on the ground. So this isn't something that would sort of ruin your view into space and stuff, right, except for astronomers. But there's a massive problem with space debris, and the fact obviously these would add to space debris, but even deploying these things in space is hard because of the space debris there. So that's a bit of a disaster. And the other disaster is to control these things, you would need supercomputers to actually sort of make sure that you were beaming light and blocking light in the right places.
Yes.
Because what you don't want is unintended climate change, unpredicted weather patterns and things like this. So you need massive supercomputers to actually control this thing. And I don't think they actually exist yet, but I think we probably will be in the realm of those type of supercomputers before we're in the realm of being able to launch these things. But I think, it'd be interesting to hear what the listeners thought about whether they thought that this kind of geoengineering is a sensible idea. I mean, I can clearly see what the bad points are, is that it's masking the real problem, isn't it? It's like our addiction to fossil fuels.
But as you say, this is just while we sort out the bigger problems, right? The root cause. Yeah.
And the problem with it is exactly the same thing happens with medicine. Imagine if your addiction to butterscotch instant whip, if the doctor was able to give you a medicine that made you feel better and got rid of some of those symptoms of your obesity, you might just carry on thinking, I'm just going to carry on eating instant whip.
Well, a lot of the planet still is, metaphorically speaking.
Yeah, exactly. So I think it would make people complacent. But I think that that's a bad argument. I think I would still try and treat you with medicine and then really try and work hard on getting you to change your lifestyle.
That's the key.
You know what I mean?
That's the key.
Yeah, that is the key, isn't it? So yeah, it's an interesting one, but it has been tried. And there's a guy called Vladimir Siromyatnikov.
Oh, wow.
Yeah, Vladimir Siromyatnikov, who's actually a brilliant Soviet designer. He helped design Vostok that carried Gagarin into space. But his main thing is designing the docking systems for Apollo Soyuz, Shuttle Mir, and the docking system that's still in use on the ISS today.
Wow.
So he's
incredible.
And so he proposed the idea of solar sails and realized that you could use these solar sails not only to sort of navigate around in space, but also to do this geoengineering. And so Znamya was born. And Znamya in Russian means banner.
Wow.
I don't know why, but there we go. And so, and I posted this picture and it was absolutely incredible. So back in 1993, in February, there was actually this Znamya test flight where a
this is the thing you put online and everyone was like, what is that? Why have I never seen it?
Yeah. So this is, well, everyone was saying, why have I never seen it? It seems to be one of those missions that was completely forgotten about. But it's spectacular mission. And when you hear about it, it's like, whoa, this is so cool.
We got a tweet from our mate Jake, didn't we, saying, how have I never seen
saying,
this?
Whoa, how come I've not seen that? Yeah, I mean, and it even got retweeted by space.com.
Oh,
so there you go. It went wild.
Hi, Mum.
So the 20-meter thin film structure, 20 meters across, was deployed from a Progress cargo spacecraft. So this Progress vehicle had already been to the Mir space station. And the whole idea was to verify this whole concept, test a structure, and actually conduct this new light experiment, which is actually extraordinary. So
that is so
while
exciting.
It was on the, it's unbelievable. I mean, while it was on the Mir space station, you had the crew of Mir, which was Manakov and Polishuk. They actually installed the Progress had docked. And then they were able to they incorporated this device onto the Progress vehicle by removing the docking mechanism. Right. So both these things had been built by your man, and they put this reflector system on and then launched the Progress vehicle away from the Mir space station. And they were able to control the Progress vehicle and deploy this thin film structure by spinning the by spinning the structure, and while it was spinning, that the centrifugal force allows the sails to kind of unfurl, and you can see this in the video. It's absolutely spectacular how it does it.
Good
and
word.
Now
that,
it's got
it?
this
Unfurl.
Yeah, it's so cool, and they were able to do this new light experiment using this Progress vehicle with this big solar mirror attached, space mirror attached, and they basically shone a light. It reflected a spotlight onto nighttime Europe, and they could see it from the Mir space station. And this bright spot was as bright as the full moon. So if you looked up, you would have seen a spot that was as bright as the full moon, nowhere near as big, but it would have been as bright. But unfortunately, it was cloudy in Europe, so they didn't see it. So this spot moved from the south of France, through Switzerland, through Germany, through the Czech Republic, through Poland, eventually disappearing in the sunlight as it went into Belarus. But apparently it was seen from the ground as flashes of light in some of these places as it moved across the landscape, including places in the German Alps and places like that. It's just like, so this thing actually worked, and not long after that, the structure was jettisoned, and apparently even then people were able to see that structure from places like Canada, and the Progress vehicle burnt up in the atmosphere. I don't really know what happened to the film structure. I'm assuming that it eventually burnt up in the atmosphere as well and followed it in. But all the other repeated attempts at this all failed. They just didn't manage to get the next version up. The next version up, when it went up, when the sails were unfurling, it snagged on the aerial and all the mirrors got ripped. And bear in mind, this was at the time when Russia... basically the collapse of the Soviet Union. It's round about that time, so it was lucky that the experiment ever went ahead in the first place, because it was conceived by the USSR and then actually deployed by the Russians. So it's lucky that it went ahead. I mean, it would have been, how cool would it have been if Helen Sharman had been the astronaut on board Mir at the time of that deployment, but she just missed out. It's actually round about that era. So yeah, that's really quite exciting. So these things are possible. They work.
I think Space Mirrors is my new favourite thing. I might have to go down a YouTube rabbit hole.
Not as many articles as you'd think, considering what an epic piece of space hardware it was. I mean, if Elon Musk had done this, we'd never hear the blooming end of it.
We are starting the resurgence, Matthew, single-handedly.
Yes, exactly. Jamie, I think we should listen to the far more sensible and greater space and science communicator. Mr.
Well, speak for yourself.
Professor.
He definitely is.
So good.
Professor
So
Jim,
good.
let's roll the tape.
Ekute.
The Interplanetary Podcast, putting the ace back into space.
So I'm joined on the podcast by Professor Jim Al-Khalili, and I'm in his office at the Department of Physics at Surrey University. Welcome to the show.
Thank you very much. Welcome to my office.
Well, it's a real pleasure. I have to say, I've not been to the Surrey campus before, even though I've worked for 3 years literally down the bottom of the road. So, which is I'm even allowed to use the university library, but I'm going to go there afterwards. But
Well, that'll be more than our students do. But not because they don't read, but because everything's online anyway. I don't know whether people don't use libraries anymore.
Yes, I know.
It's a shame.
I just love the peace that you can get.
Yes, absolutely.
It's good. Actually, I think probably the best place to start is if you can give us because it's a really interesting one, I think, your journey into becoming a physicist.
Yeah, I mean, I was never the geeky child, sort of dismantling radio sets or asking for the telescope for Christmas. My younger brother was probably more into science, knowing the names of dinosaurs and stars and so on. But I fell in love with physics in my early teens, and I realised I was good at it. I realised I was good at maths. My mum has an arts background, and so she wanted to teach me to play the piano, to read music, and to paintings and so on. And I enjoyed the art side as well. But I just found a subject like physics easy, that it was logic, it was common sense. But also because it helped me, think about some of the deep, fundamental questions about reality. And once I decided physics, well, that's the subject for me, that was it. It was a love affair that's lasted ever since. Was there any particular sort of physicists or TV programs that got you into it? Not really. I grew up in Iraq, and so I didn't we used to come over to the UK for summer holidays regularly, but I didn't settle in the UK until I was 16. And so the books that I had access to, I would borrow from the British Council Library in Baghdad. There wasn't much on TV. I mean, I enjoyed Star Trek, the original Star Trek. We're talking late 60s, early 70s. But no, so I didn't have those, growing up admiring sort of the Patrick Moores and the Johnny Balls that maybe others of my generation would have been used to had they grown up in the UK. Wow.
So then where did you actually study your because you went on presumably to do a PhD and...
Yes, here at Surrey. Here at Surrey, I sort of man and boy. After my PhD here, I went to UCL for University College London for a couple of years as a postdoctoral researcher, and then came back to Surrey because I'd specialised in theoretical nuclear physics. That was my PhD subject, and Surrey had the largest nuclear theory group in almost in Europe. So it was a place to gravitate back to, and I'm still here now.
So you're still here now, and you're still giving lectures to undergraduates?
Yes. I'm very proud of the fact that because of the nature of my work, which I guess we'll talk about, I'm not full-time here at the university every day of the week. So I don't feel that need, which a lot of academics have, for sabbatical. The year out, where you can go and pursue other things, write your book or work in some research lab somewhere else, develop your research. So I haven't had a sabbatical. So I have taught undergraduates consecutively here. Now, this is my 28th year. And without a break. I don't do that much teaching. It's not like this is all I do, but I do love the interaction with undergraduate students. It's something that I love. So you must have your modules absolutely nailed down by now. Yeah, pretty much. It's interesting. I've just returned to teaching a first year module that I did teach for many years and then gave it to colleagues. And now they've given it back to me, and it's all sort of souped up and written up in lovely lecture notes, and there's all these slides and quizzes and tests that they've put in place. Oh, what have you done to my course? So I'm now trying to get my head around the subject because I've only just started teaching. It's the second year module. I only started teaching it last week.
Yeah. So what's the name of the module?
It's called The Universe.
The Universe.
So it's pretty all encompassing. It's a first year undergraduate. So for freshers, 18-year-olds, it's the module where they learn it's the reason why I like to think they're doing a physics degree. You know, derive E equals mc squared from first principles. Why can nothing go faster than light?
Yeah.
How do we know what we know about the nature of stars and black holes and the Big Bang and so on? So it's all that cool stuff, but at a level that isn't too high. Yeah. Because of course these are first years.
Yeah. So in that, it's over 20 years you've been teaching that particular model. So presumably lots has changed in our understanding of the universe in that time.
Yes.
So is there any specific things that you could sort of go, of course we've had to change that element?
Well, I mean, certainly there's a tutorial question that I've asked the students, and which is, what is the biggest discovery or revolution in astronomy in your lifetime? And of course, the biggest one that we tend to talk about is the discovery of dark energy in 1998. Yeah. Well, that's no longer in the lifetime of these young students anymore, because it's 22 years ago. And so, well, that's before I was born. That's ancient history, they'll say. So I mean, I started teaching this course before dark energy. And so when I talked about the expansion of the universe from the Big Bang, there were the three scenarios. Either it carries on expanding forever, slowing down, or it slows down to a stop, or it recollapses in on itself in a big crunch. The notion that it will be expanding ever more quickly just wasn't part of the syllabus back then.
Yeah, that's amazing, isn't it? I mean, that really is. So what do they put now? What's in the last since then? What are the students putting now as the big discovery?
Well, now it's something like gravitational waves. I guess that's probably the most popular one. Black holes, as the famous image of the black hole that hit the news last year. So I suspect this cohort that I'm teaching now would probably use that as an example. And exoplanets. So that's also just probably, well, certainly the proliferation of exoplanets. Maybe not the first one.
It seems to me if you're getting them really excited about the universe and how it's changing, how do you keep your physics undergraduates from moving over to, say, astronomy or astrophysics? Or do you expect them to go on to do astrophysics?
Well, I mean, we do have one of our programs in the physics. We do have an astrophysics research group, including astronomers and modelers of sort of galactic formation and so on. So one of the undergraduate programs we have at the Surrey Physics Department is physics with astronomy. Yeah, and some fraction of our undergraduate cohort will be doing the physics with astronomy strand, and they'll be part of the audience that I'm teaching. But no, I try not to make it too exciting for them, so they all disappear, because I'm not an astronomer or astrophysicist. I'm a quantum physicist, so I don't want to oversell a rival part of physics.
So okay, let's go back to, so you're a quantum physicist. So what are you working on outside of the universe? What's your area of research and expertise at the moment?
Well, my background, as I mentioned, is nuclear physics. And for most of my career and most of my research papers that I've published have been in modeling nuclear reactions. So how two atomic nuclei collide and break up or fuse or scatter, and using quantum mechanics within the mathematical modelling and computer modelling to try and predict what will happen. But in recent years, I've slightly moved to one side, and now one of my big interests is actually in the foundations of quantum mechanics, called open quantum systems. So rather than studying a quantum system, a very small thing like two nuclei colliding, how does that fit into the surrounding environment, the outside world? So it brings in some really sort of foundational questions in quantum mechanics that we're still trying to wrap our heads around, like what is the nature of measurement in quantum mechanics? What does it mean? What is decoherence? What is entanglement? And that's much cooler.
Oh yeah, it's really cool. I mean, I heard a very good argument between you and another of my favourite science communicator Sean Carroll about this exact subject, which I think is very interesting. So yeah, what is your take on because I don't think we got to hear your take on where you think quantum. What you think the actual solution to quantum mechanics is, because it is a bit embarrassing, isn't it, that it's over 100 years old and we haven't really kind of answered that question.
I mean, I think there's always physicists are always very wary about overselling this crisis in our knowing what is actually going on at the quantum level, because quantum mechanics has been so incredibly successful, and it's the most powerful theory in all of science, pretty much, because it underpins so much of physics, all of chemistry, because it tells us how electrons arrange themselves in atoms, and atoms fit together to make everything. But I think going back to the founding fathers of quantum mechanics, something I discussed with John Carroll, there's been this hegemony that you're not meant to ask why and how, but how is that atom in two places at once? It works. That's what the maths predicts. The maths predicts a result that if you go and do an experiment, that's what you see. It explains the phenomena of the microscopic world so brilliantly. And a lot of physicists for generations have argued that wanting to come up with some sort of logical or rational explanation for what's going on is just pointless, and a waste of time. Just go and do philosophy if that's what you're worried about. But the people of my generation and Sean Carroll's, middle-aged physicists, our supervisors would have warned us against exploring some of these issues. They are now retiring. We are now becoming sort of the old guard. And we're becoming a bit more emboldened to ask the question, which is that the fact is the maths works, the equations work, it's absolutely solid. We're not anticipating, even if another Einstein comes along in a revolution in physics, quantum mechanics won't be shown to be wrong, right? We know that. The maths is solid. But what does it mean? We have all these different interpretations. The narrative that you attach to the maths to give it meaning, because it's meant to describe the real physical universe, independently of our squabbles. And there are these different interpretations. My view is that I am very much agnostic, because I don't know which one is correct. A physicist should not use words like "I believe that this." That's not science. All these interpretations currently make the same predictions for any experiment you choose to carry out. So you can't discriminate between them. If you believe that in the many worlds interpretation, the universe splitting into multiple parts, well, that's predicted by the maths, and the experiments, results of experiments it predicts turn out to be true, as do lots of other different interpretations.
So I mean that also, I mean, you've got this problem that you've got this wildly successful theory that just works, and like you said, it's one of those things that's not going to be rubbished. It's not going to be. It's never going to be turned away. But you've also got relativity that is incredibly successful. It's exactly the same story, really. It's every single day it seems that there's an experiment that confirms Einstein, and so including gravitational waves, and so. But these two theories, even for someone like me with a very small brain, I can see that they're not really that compatible, and that's the big struggle. So where are we at the moment with those elements of it?
Well, for the last 30 plus years, 40 years now, almost. Physicists have been looking for the so-called theory of everything that brings together quantum mechanics and relativity, a theory called a theory of quantum gravity. Because Einstein's relativity, the nature of space and time, is also the theory of the force of gravity, which replaces Newton's idea of gravity. So Einstein's view of gravity is that matter and energy warp space and time. Space and time can be curved and bent, and they tell matter and energy how to behave within them. So it's pretty sort of profound and deep and fundamental. Quantum mechanics is about the very tiniest building blocks of matter and energy in reality. And as you say, they are very different structures.
But can you? Is there a simple explanation about why they don't really kind of interact?
Einstein's theory of relativity is the theory about the structure of space and time. In quantum mechanics, space and time are sort of there from the start, and stuff happens within space and time.
Right.
But quantum mechanics doesn't tell us how space and time itself is quantized.
Right.
And general relativity talks about space and time, but it's smooth space and time. It's not bitty. It's not lumpy, which the quantum world, we're told, should be. But to give you another quick example, even something as fundamental as the nature of time itself is not understood.
Yeah.
You know, relativity theory tells us time is a dimension, like our dimensions of space. And it's the fourth dimension in 4D space-time. It's a dimension that can be stretched and bent and seen from different perspectives and so on. Quantum mechanics tells us time isn't a dimension. It says time is a parameter. It's a number that you put in your equations to predict what your system of interest is going to do in the future.
So time's not quantized, is it?
It's not quantized. No. It's just a number that puts in that allows you to see what an electron is doing. But the thing is, it's reversible in quantum mechanics. So the way a quantum system behaves now, you put in the time now, you can crank the handle and work out what that system will be doing if you were to make a measurement at some time in the future. But likewise, you could work out what it was doing in the past because time goes forwards and backwards. That's not the same in relativity. And then to make matters worse, there's a third arm in physics, which is thermodynamics, which is another topic that's not quantum and it's not relativity. And thermodynamics, the subjects about heat and statistical mechanics, their time has a different definition. It's an arrow pointing from past to future. So if these three pillars of physics of the 20th century and indeed the 19th century, thermodynamics, quantum mechanics and relativity, all have completely different ways of explaining the nature of time, then you realize there's something missing because they can't all be right.
Yeah.
And so, you know, is one wrong? Are they all wrong? We don't know.
Yeah. So where does something like information theory, because like someone coming outside of physics and coming straight back into it, you hear about information theory quite a lot and how important that's become in the last sort of decades.
Yes. So there are various aspects to it. So in particular, quantum information theory. In quantum mechanics, information cannot be destroyed. There's like a conservation law regarding information. But in relativity theory, there's an issue. This is something that Stephen Hawking grappled with, that, you know, if you throw a book into a black hole, yes, the matter that makes up the book will all be squashed down to the singularity in the middle of the black hole. But what happens to the information? And you might think, well, you know, it's lost. But quantum mechanics doesn't allow us to lose information. So chucking books into black holes is exactly one of those examples where quantum mechanics comes face to face, colliding with relativity theory. So we know that things like information and the leaking of information in quantum mechanics, when you make a measurement of something, when you open Schrodinger's cat's box to see if it's dead and alive, you're gaining information. So the information comes in when we're talking about the measurement process in quantum mechanics. And the way quantum information dissipates into the surrounding environment is that somehow similar to the way heat dissipates from a hot object into a colder surrounding environment. So that brings quantum mechanics and thermodynamics together. So I'm throwing these examples around because we don't know how it all fits together. We sort of have hints and clues, connections between these different subjects, but we also realise we're a long way from that final collection together.
Yeah, because I'm right in saying that Hawking was quite close with his evaporating black holes, Hawking radiation, because that has got a little bit of quantum theory and a little bit of relativity in there.
That absolutely, and a bit of thermodynamics because it has this quantity called entropy. You know, the amount of disorder, which is to do with information. So yes, it's a very neat sort of collection of all these subjects together, but it's not verified experimentally. It's really hard to check that these black holes really do give out what we now call Hawking radiation. If we could discover that, or if we could have done while Hawking was alive, he would no doubt have been given the Nobel Prize. But of course, it's too late now.
So presumably, so something like Hawking radiation, it's just really, really hard to measure it. Is there a timeline where something like that would be measurable? Are people working on it, or is it something that's so faint, really, that
I think it's not something that we could carry out an experiment directly to detect, to confirm. It's a bit like, ideas like, is gravity, if gravity is quantized, it'll be made of particles called gravitons. Well, are we able to detect gravitons or make them in a laboratory? And again, we're so far from being able to design an experiment that would directly probe and confirm these ideas, that physicists realize there has to be a bit more imaginative. We'll have to find indirect ways of testing some of these ideas.
Yeah, so actually that's a really neat point about, if as a theoretical physicist, you've obviously got things like the Large Hadron Collider and stuff like that as laboratories. But presumably space itself is this fantastic laboratory as well for testing ideas, because you can look at quasars and look at black holes and look at all these other things. Is that something that's become like really important to physicists? The information that comes from, say, Gaia or these space observers?
Yes, I mean, I think, the example of the discovery that there's something pushing space apart, which we now call dark energy, discovered back in 1998, is a good example of that. It wasn't expected. It was detected by astronomers looking at the recession speeds, how fast distant galaxies are moving away from us, by looking at those galaxies that have supernovae, exploding stars, because there's certain types of supernovae that explode with a certain brightness that gives you a very reliable measure of distance. And so they're just doing astronomy, and yet they discovered from the speeds that these galaxies are moving away from us that the universe expansion is speeding up. And then that tells you there's this thing, dark energy, that's pushing these apart. What is dark energy? You start then going back to your equations and trying to figure out what the origin of it is. And now people talk about it being the so-called quantum vacuum. So you're now learning stuff about the quantum world, having looked through your telescope. So it is bringing in, that what's out there might help us understand the reality at the tinier scales.
I'm really fascinated by that connection. I mean, who tracks it? If you've got physicists who may be just looking at their own work, or mathematicians just doing their equations, who tracks and goes, oh, hang on a second, this guy with his telescope has just found something really interesting that relates to what I'm doing. It seems to me that you have to have these kind of enormous cross-discipline mindset to make that connection from this guy over here has done this.
Well, I think it's true, certainly. If all physicists and astronomers and cosmologists stuck to their own discipline and didn't talk to each other, those connections wouldn't be made. But I don't think it requires someone with a polymath spanning all these areas. Physicists talk to each other in departments, and it was probably decades ago that particle physicists and astrophysicists starting to say, hang on a minute, if we do this, we could check that. And in astrophysics, if they're wanting to understand the nature of dark energy or dark matter, they know that they have to talk to the particle physicists. That's one way of discovering what this stuff is made of.
Is this the sort of thing that happens in the canteen, or?
Yes, it's the canteen, over coffee, at conferences. It depends on the sort of the collegiality and the atmosphere within research institutions and university departments. But physicists talk to each other.
So we've got this we've got this little problem with gravity and quantum mechanics, but we've also obviously in the last, like you said, in the last 23 years, I suppose, is dark energy and of course dark matter as well. So we've got these two almost, I would say, embarrassing things that relate to physics and cosmology that we just don't seem to have a proper handle on them. What would be your hunch for, say, something like dark matter? We spent the last two episodes talking about dark matter, so it'd be good to get an expert opinion on dark matter.
I mean, I would say expert. Actually, the chap in the office next door to me, Justin Reed, who is head of the physics department here at Surrey, is a world-leading expert on dark matter. So as long as he can't hear me through the walls, he'll
come running through.
That's not right. But yes, I mean, dark matter is one of those subjects where, you know, we know it exists. That there is really, absolutely, almost universal consensus that dark matter is real and it's out there. And we've tried different ways of working out what it's made of, either by looking through our telescopes and looking at how dark matter is causing normal matter to behave, or to how it bends light and so on. Or we put detectors here on Earth to try and capture dark matter, or we try and create it in our particle accelerators like the Large Hadron Collider. All those three attempts so far have come up empty-handed. And it is getting to the point where we're getting sort of quite frustrated. What more do we have to do to find what dark matter is made of? There's all these candidates that theoretical physicists have proposed could be the ingredients of dark matter, but we don't know which one of them, or indeed if any of them are correct. We know dark matter isn't made of anything we currently have, that we currently know. It's not made of normal quarks or electrons or the particles that we know of. It must be something else. But we also are not going to give up on it. People might think, well, okay, look, if you haven't found it, here's a possibility. It doesn't exist.
It's like the opposite of if it is a chicken.
Yeah.
Like a chicken.
That is a chicken. Well, if it's nothing like a chicken and it doesn't, it doesn't cluck, and doesn't, then it's not a chicken.
Yeah.
But there's too much evidence that dark matter's there, and it's absolutely in-your-face evidence. You see how light from distant galaxies is bent by closer galaxies to us, but bent far more than the matter that galaxy is made of, all the stars that galaxy is made of, can account for. And it's bent in a way that suggests there's an invisible halo of stuff that we don't see, hence the name dark matter, that is causing that light to bend. But also, we cannot explain the universe and its structure now without dark matter. We now believe that galaxies could not have formed in the first place were it not for the help from dark matter, which clumped together before normal matter did. And so there's lots of evidence from astronomy and observations that really tell astrophysicists that dark matter is there. What it's made of, well, we're still waiting to see, and say there are various candidates.
So in terms of like the main body of physicists, etc., that they think that it's a physical matter rather than, say, one of these modified gravity theories.
Yeah, that's right. I mean, there was for a while this push that if we just tweaked Newton's law of gravitation or Einstein's field equations of general relativity, you add another term or you change some numbers, then you can account for dark matter without postulating some new stuff.
Yeah,
that doesn't work. I have asked that very question of colleagues who work in dark matter. Why can't that be a possibility? And they will tell you that, for example, we now have very detailed information about the structure of the very early universe, the cosmic microwave background, which is the fluctuations in the temperature of deep space that were an imprint of the very early universe. And some of the properties of that cosmic microwave background are very well established and are explained beautifully with dark matter, but are not explained by these modified the MOND theories that modify the equations of gravity. So, we would like to be able to put this to bed, and it's not like it's a conspiracy or dogmatism that we will not listen to something else because we have some vested interest in looking for particles of dark matter. No, if the equations, for me as a theoretical physicist, if the equations could be tweaked to account for dark matter, brilliant. Then we can all stop wasting money designing experiments to look for something that doesn't exist. Yeah. But the fact is, I think we're still pretty persuaded that it does.
Yeah, I mean, would you suspect that if someone cracked a quantum gravity theory, a theory of everything, that things like dark energy and dark matter would be within moments revealed to be what they are, or would that not work?
No, I think it should do. I think our current we currently have two what are called standard models in modern physics. One is the standard model of particle physics, which tells us all about the building blocks of matter, from quarks and gluons, electrons, all the way to the Higgs boson. And the other is a standard model of cosmology, which flows from Einstein's theory of relativity. But we don't know how dark matter and dark energy fits into either of those. And so the assumption is that if we do arrive at a theory of quantum gravity, it will be a theory that brings together the standard model of particle physics and the standard model of cosmology, what's called the concordance model. And inevitably one would hope that in for free would be an explanation of what dark matter and dark energy are. It wouldn't be a theory of everything if it didn't account for these two very important aspects of reality.
I mean, how likely do you think a theory of everything is, or is there a possibility that you could get to a point where you actually can't get to a theory of everything?
Well,
I mean, I know it's a bit of a philosophical question.
No, it's certainly true that there's no guarantee that we're going to arrive at a theory of everything. But the fact is, there has to be a way of bringing these two things together, quantum mechanics and relativity. And to give you a simple example, general relativity it tells us how space and time reacts to matter within it. Imagine that matter is an electron. Imagine that electron is in a superposition of being in two places at once. Then those two regions of space-time will also be in a superposition. They'll both be modified at the same time. Yeah. So space-time has to reflect the fuzziness of the quantum world because it contains within it matter that will behave quantum mechanically. So there must be a way of explaining it. That is such a tiny effect because gravity is so much weaker than the other forces that we've no way of measuring some change in the structure of space-time because of an electron being in a superposition of two positions. But that should still happen. So the fact is quantum mechanics works in its domain, relativity works in its domain, because there are very few examples where the two clash and you have to use them together. But there must be an explanation for that. It doesn't mean we are going to find it anytime soon, though. Yeah.
Is there any kind of hints that people are on the right way? I mean, think something like superstring theory string theory it sort of came with a flash, didn't it? And it died away again. Is there one of these things that seems to be making progress? Or
I think, certainly there are many very smart string theorists out there still working on it who might, pick you up on the fact that string theory's faded away, died a death. They say it's still, it's still healthy. But it is true. I mean, that string theory developed in the 80s, mid 80s, and then further in the mid 90s. Was seen as the leading candidate for a theory of everything, and many people working in the field thought that it would. We just cross some I's, dot some T's. No, other way around. Dot the I's and cross the T's.
Maybe that's what happened.
Maybe that's what they did. That's where they went wrong. Yes, but that hasn't happened. I think now the broad consensus view, if you take an average of all physicists' views, is that string theory is a very powerful mathematical tool. It's led us to an understanding of not just heading towards a theory of everything, but it's had applications in other areas of physics, like condensed matter physics, the structure, the properties of material in bulk. So it's very useful, but a useful mathematical tool is not the same as a theory or description of reality, a theory of everything. And of course there are other rival, the big rival to string theory was what's called loop quantum gravity. Loop quantum gravity is a way of quantizing space-time gravitational field, which is also, there are still people working in it, and it also hasn't sort of maybe made the progress people hoped. But there are a number of physicists and cosmologists and particle theorists who are now thinking, well, maybe we need to take a step further back. Clearly, we're not making the progress we'd hoped. Are there different ways of approaching it? And that's one of the reasons why, for example, foundations of quantum mechanics, the interpretations of quantum mechanics, are starting to come back in fashion again, because there is this feeling, which is not really how science should work, but the sense that to arrive at a theory of everything, we also need to find the correct interpretation of quantum mechanics. You know, whether it's many worlds theory, whether it's hidden variables theory, whether it's relational quantum mechanics, cubism. There's all these sorts of, spontaneous collapse theories. Yeah. Wonderful array of names of ways of explaining the weirdness of quantum mechanics. And until now, that's just been philosophical, right? Because quantum mechanics works, who cares? It's what day of the week is it? Right, today I believe in this interpretation. Now we're coming around to the possibility that maybe in order to solve a theory of everything problem, we also need to solve the problems in the foundations of quantum mechanics.
Yeah, so I guess the analogy to that would be, it requires an Einstein to sort of step back and sort of see a deeper relationship and then go back in and everything falls into place like it seemed to do.
I think to some extent that's right. Maybe we are waiting for the next Einstein to come along, and that next Einstein may actually be artificial intelligence, by the way.
Yeah.
But my hunch is that with Einstein, his revolution, certainly for special relativity in the early 20th century, where he said all observers see light traveling at the same speed. The speed of light is invariant, and it doesn't have a medium to travel through. And from there, that gave an explanation of the equations, what are called the Lorentz transformation equations. So the maths, again, for relativity, the maths was in place before Einstein. Yeah. He didn't come up with the maths. He's credited with the discovery of special relativity because he attached the correct interpretation to the equations.
Yeah.
And it really beggars belief. I'm astonished that physicists around the world seem not to have made that connection. That, why has quantum mechanics got away with it?
Yeah.
Einstein credited with relativity because he found the correct interpretation, not Lorentz or Fitzgerald or Poincaré, who were the mathematical physicists before him who came up with the equations. We're at the stage in quantum mechanics that the equations all work, but we seem not to care how or why or what they mean. And so, coming back to your question about, are we likely to get to a theory of everything, and do we need another Einstein? Einstein's revolutionary idea was actually quite simple. I teach it to my first year students, that there's two postulates of special relativity. One is all motion is relative, and that goes all the way back to Galileo. And the other is the speed of light is the same for everyone, however fast you're moving. From there, everything else unfolds. My hunch is that there isn't anything as simple as that's going to lead us to a theory of everything. I suspect it's pretty complicated. and so it may not be an Einstein, it may be a lot of people
crunching away.
In the same way that quantum mechanics wasn't down to one person.
Yeah.
Heisenberg with his uncertainty principle, Schrodinger's equation, Pauli's exclusion principle, Paul Dirac saying, well, this idea and that idea, bring them together and you get this. So there's a whole group of geniuses in the 1920s who between them put quantum mechanics, the foundations, the maths of it together. We're going to need that, I think, large group of thinkers to progress towards a theory of everything. Not one revolutionary genius and everyone's going, of course, yeah, you're right, didn't occur to us.
Yeah, because you kind of get the impression that Einstein himself was a little bit upset by the shut up and calculate philosophy.
Yes, well, I mean, you can very broadly divide the views about quantum mechanics into two camps: the realists and the positivists is another way. Or in what philosophy would call epistemology or ontology. So. Or put it in terms of people, you've got Einstein versus Bohr.
Yeah.
So Einstein believed there was a physical reality out there, and it's job of physicists to understand that physical reality. Bohr said, no, the job of physics is only to what we can say, the state of our knowledge about physical reality. We can't describe reality itself directly. All our equations tell us is what we can say about reality. And there doesn't need to be an objective reality out there at all. All quantum mechanics gives us is the tools to predict the outcomes of experiments. And Einstein said, no, that's not enough. I want to know what's going on before I do the experiment, before I do my measurement. And Bohr would say, well, that's pointless, because how do you know whether you're right or wrong unless you do the experiment? So it's a philosophical view, but I side with Einstein. For me, I think the job of physicists is to understand physical reality, which is there. It exists independently of our puny brains, arguing about it. And we should be able to get as close as possible. We may not ever actually get an exact description of reality, but that ultimate truth is there. It's waiting for us. And those physicists who say, no, it's a waste of time, all quantum mechanics does is give us the tool to make predictions of experiments, that's not physics. Yeah. That's engineering.
Yeah.
And I don't want to insult engineers, but engineers don't care about the how and the why by a large extent. They want to know if it works, I want to use it and apply it and do something useful with it.
Yeah.
Whereas a physicist wants to know how it works and why it works. And for generations now, I think practitioners in quantum mechanics have sort of forgotten what the job of physics is about.
Do you think? So you were saying, right back to your very early point, that seems to be a generational thing that as we're moving into this, the sort of the people that were taught by Bohr, and then they're the kind of last of that old.
I think that's right. I was taught what's called the Copenhagen interpretation, which is the standard view. That's what all quantum mechanics textbooks are at universities all around the world, still to this day. And that's the view that was promoted by Bohr and Heisenberg and Pauli, which is to say that here's the maths, here's quantum mechanics, it works. Don't worry about how that electron can actually be in two places at once. You use the maths to make predictions of what you will get when you look. And certainly the students of Bohr and Heisenberg and Pauli and Dirac were also promoting that hegemony, that view. My PhD supervisors, who are now retired, would have also been on that view. I, as a PhD student, was a pain in the butt. I would, but why? But how? That can't be. But and others of my generation were also like that. And I think we're now at the stage where this area called Foundations of Quantum Mechanics is undergoing a real revival and starting to make progress, partly because we can now do very careful experiments that we were unable to do before to test some of these ideas. Really, really precise experiments in quantum optics and so on. But also because we've moved out of the shadow. We are now sort of, I think, confident enough to say, no, hang on a minute, this is, I wouldn't have used this language or been as bullish as I am here now 25, 30 years ago. When I was starting off as a researcher, I would have bowed to greater, more wise people. I sort of feel that courage that I can say these things more clearly now.
So you've got this kind of double whammy effect of your generation, getting the courage to sort of get to that point, but also that the experimentalists are actually able to kind of back up some of these ideas. Yeah. You can kind of see that the generation before and the generation before that would think, well, there's no way of even coming close.
Exactly. So why waste your time? Because what they would have thought was just pure philosophical speculation, we can actually now test, and we are starting to make slow progress. We're not there yet. We still don't know if many worlds interpretation is right or not.
Do you think that because I want to talk about your science advocacy and how you go out and present, because you're one, as I've said, you're one of my favourite science communicators. Do you think that that's helped you be a science communicator? That kind of sort of new openness to trying to find out those ideas and confidence that.
I don't know. I've always enjoyed explaining. That's because of the nature of my work as an academic, as a researcher, as a broadcaster, as a writer, as a speaker. The common thread is that I'm an explainer, and not all physicists, not all scientists are like that. Many would like to learn about the world, how the world works, solving their equations, writing their codes, publishing their papers, and that gives them enough pleasure. For me, I derive as much pleasure as that, finding out for myself. I also get as much pleasure by shouting about it to the rest of the world, to anyone who will listen. And so I've always enjoyed this. It wasn't something that grew as I grew in confidence in my own knowledge and ability, because I think maybe I surrounded myself, my social group of friends weren't physicists, and so I was very used to having to explain to them what I was doing in plain language. And I think it's more to do with science communication, or any sort of communication of a complex discipline, is about empathizing with the person you're talking to. Put yourself in their shoes. How do they see this concept that you're trying to explain? So it's picking the right language, picking the right analogies and examples, and being aware when that light bulb goes on over their heads, and you think, okay, your penny's dropped, to mix my metaphors. Now I've hit it. I've found the right way of explaining it.
Yeah, because I mean, in my own personal practice as a lecturer, I've noticed that I feel as though I don't truly understand a subject until I try to teach it.
Yes, no, that's very true. Absolutely. Teaching the subject realizes that you just can't you can't make things up as you go along. They will sniff it out.
Oh God, yeah. I've been in that situation more times than not.
Yeah, no, it's very useful. To have to teach something.
Well, it's been a brilliant chat. It's been like a really great overview of where we are with physics at the moment. I've got a couple of banalish questions near the end, if you've got time. If you were to bring back a physicist or anyone from the past to either come back and show them how far we've got, or to actually help with trying to solve stuff, is there any kind of person that you would think of off the top of your head who was?
There are so many, I have so many heroes in physics, and I was sort of always inspired in when I was studying physics by reading the biographies of some of the great physicists. But there would have been people like Einstein and Feynman and Bohr and Paul Dirac and so on. I think I'd like to go further back, a lot further back. One of the greatest thinkers in the history of humanity is Aristotle. And Aristotle had such a clear view about the nature of reality, and he would make all these great observations, and he would try and figure out the nature of the vacuum and the nature of space, and so I don't know what, wouldn't it be great to bring Aristotle back and show him how much we've advanced in over 2,000 years? Blowing Aristotle's mind would be a pretty cool thing to do. Yeah,
that's a really good one. And we've got a space playlist. Is there any track that you'd quite like to add into the space playlist that for you sums up space?
Sums up space itself. Well, I mean, I love sci-fi movies, and I guess probably my favourite, as with many people, it would be Arthur C. Clarke's 2001: A Space Odyssey. So I would imagine the theme tune for that, which is "Thus Spake Zarathustra."
Yep.
Doom, 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 doom. I mean, for me, that personifies the adventure of exploring the vastness of space.
Yeah, agreed. It's absolutely. It's a banging tune.
Good, glad you like it.
Yeah, absolutely. Well, thanks very much. Is there anything that you'd like to kind of add in, or?
Well, it would be remiss of me not to mention that I have a new book out.
Oh,
of
yes,
course,
no,
right,
totally,
right.
Yes,
so and in fact, a lot of these arguments and points I've been making, to some extent, I have them at my fingertips because they are what I'm talking about in my new book. So it's called The World According to Physics. Right. And it's coming out depending on when this podcast goes out. But anyway, it comes out 10th of March. And it's a small book. It's sort of very neat and tiny, sort of Bible-sized book. But it's the Bible of physics. I say it's my ode to physics. So I'm very looking forward to seeing what how people take it.
Yeah, how long has that taken you? Is it?
It's not a huge tome. No, it's 50,000 words. So it's not a large book. Nor is it sort of like exploring the whole history of physics. It's basically, how do we know what we know now? How do we know that there's dark matter? How do we know there's dark energy? How close are we to theory of everything? Are we any closer to understanding what's going on in the quantum mechanics? And so all those ideas, I get a bit polemical in the book, but it's sort of I always say if we think about all the knowledge we have of the physical universe is an island, and we're surrounded by the ocean of the unknown. Well, this book is exploring the shoreline, right? Not how we got there. It's exploring that, the boundary between what we know and what we don't know. But it doesn't tell you how far the ocean extends to. Does it go on forever? Will we one day know everything, or will we always be peeling back layers of the onion? That's one thing we can't answer yet.
Yeah, brilliant. Well, I'll definitely look out for that book. And I've absolutely loved your books before, and
I hope you enjoy this one too.
I absolutely would, I'm sure. Thank you very much.
Pleasure.
The Interplanetary Podcast is alive!
See what I mean, Jamie?
Well,
It's
just
awesome, huh?
epic in every way. Thank you, Professor Jim. You are our favourite professor
Wow.
of the week. Only kidding.
Of the week.
Only
Favourite
kidding. I
professor
think
of the week.
well, he's definitely in our top 3. Let's say that.
Ooh. Now, Jamie, I want to bring up, just before we go, another
on.
environmental piece of environmentalism.
Go on.
So, we joked last week about the new Sutherland Space Hub planning permission.
Yes.
And how the picture looked a little bit underwhelming.
Yes.
I've since kind of rode back on that, because I decided to have a look at the actual planning permission document, and you would not believe how big this thing is and how much detail has gone into it. So
wow.
There's all these visualizations about what it will look like from various places.
Okay.
So the whole idea is that it just disappears into the landscape, so it doesn't ruin the landscape, and you can see what it would look like from all these various vantage points, and you basically can't see it. But since the last podcast, there's been a development, and it's all to do with Extinction Rebellion, and Extinction Rebellion have decided that they don't want Sutherland Spaceport, so they have mobilized their huge army of environmental activists to basically spam the planning permission for the Sutherland Spaceport.
Right.
But in the meantime, I found a Sutherland Spaceport facts sheet, which I shall be putting on as a link in the show notes.
Yeah, let's share that.
It's Sutherland Spaceportfacts.wordpress.com, and I think this is definitely worth reading through. And I think genuinely, if you want to see a space launch from the UK, and personally on the kind of balance of evidence, I would say, look, space is going to be a really important part of global climate change.
For sure.
We only really know about global climate change because of satellites and the instruments that we put into space.
Right. And
to have a small satellite launch capability to be able to put up quick response satellites and things like that to monitor disaster, climate disasters and things like that, I think is very, very important.
Agreed.
And the environmental impact, as far as I can see, is absolutely tiny. And all the actual reality is that these satellites are going to get launched, and I'd rather them be launched from a country like the UK, where we have pretty strict environmental controls, and we actually give a monkeys about the situation. I'd rather it be here so that we can control it a little bit more. So personally, I think I'm going to go over to the planning permission and put my penny worth in, and because it'd be quite good to mobilise our fans, wouldn't it, against the Extinction Rebellion? Even though I've got a lot of time for Extinction Rebellion.
Yeah, I was going to say we shouldn't make this a us versus them thing. It should be, as you said, it should be what are the facts.
Exactly.
That.
And
what are the facts?
Here it is. We're a science-based podcast, and I think that when it comes to particularly global climate change, we really need to drop the emotion and speak to the scientists and speak to what's
speak to the experts. Exactly.
Let's actually deal in facts and not emotion when it comes to something as important as the entire world slowly drifting into disaster.
Facts, not emotion, people. Let's do this.
Yeah. So there's some. I've shared that link with the concerns of Extinction Rebellion and how a lot of them are just fake news, Jamie. Fake news.
Well,
so,
we can all get caught up in it. So
certainly can.
Let's have a look at that. So Matt,
so
what are you up to this weekend?
I'm up to watching my kids in bands again, which seems to be the only thing I do these days.
What kind of music are we talking? Any prog rock of your own heart?
No, they tend to play sort of bluesy rock and Queen numbers.
Sick.
Which is quite cool.
Yeah,
quite
totally.
Cool. Yeah. What about yourself, Jamie?
I'm probably going to go against everything you've said in this podcast and get myself a double helping of butterscotch pudding.
You
know, just sit in front of the telly emitting emissions.
Excellent. Well, Jamie, this has been a pleasure as always.
It has. Look after yourself. And Matt, have you got any advice for someone who might be listening to this podcast who's a newbie?
Yeah, if you're a newbie, join our legion of fans over on patreon.com/interplanetary or go to our website, interplanetary.org.uk, and you'll find lots of stuff. That I always try and make the show notes as readable as possible. Sometimes they're a bit of a mess, but
but hey,
they're pretty good.
Bit of a
they're
mess.
Pretty good. I think they're better than most people's show notes. I know I don't want to brag or anything, but it's so it's a good place to go. Lots of links, lots of pictures of some of the stuff we've been talking about, and we'd love you to join us on Patreon because the Patreon is the only way that supports this podcast.
We
genuinely
thank you.
Without
we love
it,
you. Thank you for your support.
We would fold.
Yeah, exactly.
Absolutely.
So those are that nothing that you just said is fake news. It's all hard facts brought to you from a couple of players who love you very much. I'll see you soon.
See you in a bit, Spotcats. Bye.
Bye.